everyone. We'll get started on the third day of the quantum algorithms workshop, and we're going to start out with Garnet Chen, who's going to tell us about quantum algorithms in chemistry and materials.
Okay. Oh, it's on. Wow. Okay, great. Okay, well, thanks for inviting me to participate in this workshop. There's many faces here I've not seen before. It's not my usual community, so maybe I'll just say a little bit about myself. So I'm not a quantum computer scientist. I wouldn't say that I work on quantum algorithms, even though that's what's on the title of my talk. So my main area of expertise is really in the classical side of simulation, developing classical algorithms for chemistry and material science. But in recent times, it's unavoidable to have some interest in what's going on in the quantum field. But in any case, I'm here to learn and to sort of exchange ideas, and I look forward to learning from all of you. Okay, so really today's talk is going to touch on a few different points. So since I'm one of the classical people, I will be telling you a little bit about what the state of the art is in classical simulations of chemistry and materials. And in that context, I'll give some opinion about where one might think of, or how one might think of quantum advantage in this setting. Then I will talk about sort of the two problems that I am thinking about in the quantum area. The first is, given these amazing devices that are being built for us by these amazing institutions and companies, can we actually use them to do a simulation and generate an answer that's not complete garbage? This doesn't seem like the highest bar, but I actually think it's quite difficult. And so I think this is what we're going to try and do to start out. And for this, I will tell you about some of the algorithms that we've been thinking about to execute on NISQ devices, and maybe they'll be useful beyond as well. And then finally, the second thing that I'm thinking about these days is a question of whether there's any task, even if it's a little bit artificial, in the chemical and material science sphere, where we can demonstrate clearly the benefit of using a quantum computer. And this is what one might call physical quantum supremacy, and I'll just touch on this point at the very end. Okay, but let me just first start with the beginning. This topic is really, this session is really about quantum simulation. And one always shows this quote from Feynman. It's taken from his talk, Simulating Physics with Computers. And like many of the things that Feynman said in his later years, it's both like very forward-looking, but also not very precise. But in any case, we view this as the start of the field. And what's really behind this is the sense that when one is dealing with molecules or materials, they are quantum objects. In particular, the electrons are very light, and so you have to describe them with quantum mechanics. And so if one were to think about the information to specify some arbitrary quantum state of a molecule or material, then the amount of classical information clearly grows exponentially with the system size. So this is the reason behind the intense interest and optimism with respect to using quantum devices to simulate molecules. So this is one side of the coin. But there's another side of the coin, and that's the following, which is that if it were really true that you needed a quantum computer to understand anything about molecules or materials, right? So in other words, if a chemist and physicist had been waiting 300 years for a quantum computer to be built before they could say anything about these systems, then these disciplines would not exist. So I think understanding the role of quantum computing in chemistry and material science is really sort of understanding the tension between these two statements, and that's what one has to resolve. So, okay, so I'll begin now by showing you some examples of simulations that one does, with classical techniques, which gives some insight into sort of where the boundary is between these two things. Are molecules really very hard, or are they somehow very easy? Okay, so let's just first start with some small molecules, and I'll show you some data from a recent benchmark. So this was a large collaboration with many, many scientists. I'm somewhere in the middle of this thing. And we just took some small diatomic molecules, which consist of one transition metal atom and one oxygen atom. Okay, so these are what we call transition metal monoxides. And the goal was to solve the Schrödinger equation as accurately as possible for these molecules with a variety of techniques. So immediately in this problem, one sees if one just looks at the size of the Hilbert space that one's considering, in the simulations that we did, it's sort of ridiculously large, right? So in the largest simulations, in the particular basis, now the Hilbert space dimension is 10 to the 44, okay? So you would argue that if you're just measuring the complexity of the molecule by the potential size of the Hilbert space that it could inhabit, this is something that's impossible. But in reality, one can do quite well, right? So this is a correlation plot of the estimates of the exact energies from a variety of different methods. In particular, these three methods here are considered to be exact in the sense that there's some parameter where if you keep pushing it, you'll get to the right answer if you put enough effort in. And it's color-coded. I don't know how clear it is, but these off-diagonal elements show you how close these estimates are, and this is on a log scale, so these bars means that the difference between the estimated total energy between these two methods is less than sort of 10 to the minus 3 atomic units. Okay? So they're very, very close. Okay, they're essentially exact. Now, is that a large number or a small number? I mean, you have to be in the field to really know. Total energies are not an observable quantity of a molecule. But what is observable in a molecule, what you can measure by experiments, are relative energies. The dissociation energy, for example, is a difference of two energies. And so we can compare these predictions to compute to the measured experimental dissociation energies. And I'm sorry for the resolution of this plot here. I just noticed this just now. But here are three methods taken from this table. They produce three estimates of the dissociation energies. This one has some statistical noise. That's why it's presented as a band. And it's plotted against the experimental measurements. So the experimental measurements are these dots here as a function of time, okay, function of year. So experiment itself is a shifting target, it's a moving target. You notice that the measurement is changing over time. But the spread of the experimental results is in fact larger than the spread of the theoretical estimates. And so what one can say from this study is that in small molecules, the best methods agree to 10 to the minus 3 atomic units, is 1 millihartree. And this is a small number in the sense that it's as accurate or more accurate than you can get from experiment. Okay, so one might say, okay, this is a small molecule, even though there's a large Hilbert space, but maybe it's simple because it's small. So one can try and do something that's more complicated, look at larger molecules and more complex chemistry.
Why isn't the Hilbert space infinite?
Oh, yes. Well, of course, we can't simulate an infinite space in any simulation. So yes, the Hilbert space is actually infinite, yes. Yeah, it's a continuum problem. I'm just showing the largest discretization we used.
But it was 2 to the 10 to the what?
10 to the 44, right? This is an...
10 to the 44.
Yeah.
You actually discretized.
Yeah, we actually discretized it. This is the size of the space. Yeah. It's actually infinite in reality. This is, this is we are approximating infinity by this number. Yeah. So one can look at, perhaps some more complex systems. And, one example of a complex system that appears to be known in this field, in the quantum computing field, is nitrogenase. Okay, so nitrogenase is an enzyme that, it takes atmospheric nitrogen, converts it to ammonia. It's very important in the biological nitrogen cycle. It's actually two pieces of this. I've just chopped it in half. And there are these three central machines in this cluster, which in this enzyme, which are known as iron sulfur clusters. So there's this piece, the P cluster, and this M cluster here. And these systems are considered to be kind of complicated to simulate because the traditional wisdom is that transition metals are relatively complicated chemical objects. And so if you were to take a system which has many transition metals, then it must be more complicated. And the example in biology of a system which has the most transition metals that's doing something interesting is this protein here, is this enzyme here. And so I think for that reason, in this, I think, very well-known paper by the Microsoft group, I suppose, nitrogenase, understanding the electronic structure of nitrogenase is described as the killer app for quantum computers. But although it's true that this system is very complicated, it's not the case that one can't actually do anything classically or that one doesn't have any classical understanding of the system. And so, here's an example of a calculation on the P cluster, the second cluster here, where one computes the various excited states that are involved in the chemistry of the system. And here are the energies that one obtains. And the energies that one gets are not, the errors are not as small as in the last case because the molecule is much bigger. I mean, they're roughly 10 times as large. But one can do a little bit of extrapolation and so on and get some estimates, which are now, again, back on the 10 to the minus 3 scale. Okay, So that means that, even in these very complicated systems, at least semi-quantitative insight is possible. And then finally, I'll just say a little bit about materials. I mean, you could show lots and lots of these slides. Often when one's talking about the physics of correlated materials, one talks about them in terms of models. Perhaps the most famous model is the Hubbard model. Nowadays, I guess people call it the Fermi-Hubbard model. And this is a simple Hamiltonian which has a parameter in it which controls the strength of the Coulomb interaction. And if you simulate this model, and you change this parameter around, and you change the density of particles in the model, so you change the number of particles entering into it, then it's believed to produce at least all the typically seen phases, electronic phases that you have in materials that you can make. Okay, so people have some understanding of the complexity of this model in the sense that they know that for certain parameter regimes and certain densities, it's kind of difficult to get a very good answer. And so one way to see how well we understand or how well we can simulate things is to try and just take these most difficult points. And that's something that, I was going to say experimentalists study this as well in quantum emulations. So one thing we did was look at the Hubbard model at one of these difficult points, at this 1/8 doping point. This is a paper which is mainly about the physics at this point, but there's a lot of numerical data, so we can use it to extract some benchmarks. And one sees that by applying all these variety of methods, one can get some agreement in the total energy of the system within an error bar of about 0.5%. So that represents the sort of accuracy with which we understand some of the most difficult materials models today. Is 0.5% or 1% a big or small number? Well, it depends on what you're interested in. So, if I translate this into temperature for a material described by this model, such as a qubit material, then that's a temperature of about 30 Kelvin. And so physics that is on scales that's smaller than 30 Kelvin will not be resolvable. But there's a lot of physics on scales that are larger than 30 Kelvin, and that can now be accessed. Okay. So from these slides, I think it's clear that the right way to measure complexity in chemical material systems is not the size of the Hilbert space. That's a sort of a too naive a metric. Instead, when one's thinking about all these different classical simulation methods, there are many other axes of complexities that one use. And the reason why there's so many different acronyms I showed on those slides, which I didn't explain, these are all different classical techniques, is because they have different performance and different they have different, they get to different points on these various axes of complexity by which you can describe different problems. So some examples, and this won't be exhaustive, is you could classify problems by their dimensionality. There are many methods that just work in all dimensions equally well, but there are also many methods that are particularly good only in certain dimensions. Some methods actually don't scale at all with the dimension, right? Some methods are particularly efficient in one dimension. Some methods work in all dimensions. Similarly, you might think about problems in terms of how much order there is in the quantum state, how close the correlations are in some sense to classical. Diagrammatic methods typically work very, very well, Feynman diagrams, when you're close to an ordered state, and they break down as the system becomes frustrated. If you're someone who likes random numbers, then you want those random numbers to all come out with the same sign, right? If you're doing Monte Carlo, so you don't have a lot of variance. And so in that setting, the magnitude of the sign problem is very important in defining the complexity of the system. And then, another axis is how realistic your model is. So there are many methods which work really well in the sense they produce very accurate solutions of the Schrödinger equation, but that's only for Hamiltonians, or at least they're only practical to apply if the Hamiltonian doesn't have many terms in it. And if you want to do with more realistic systems, then you might choose to use methods which don't give as an exact solution of the Schrödinger equation, but can deal with lots and lots of terms. Okay. So what this illustrates is at least the way we think about all these different problems in chemistry and material science is that when designs a strategy for the problems of interest, these strategies are typically very problem specific. So there's a lot of heuristics and empirical knowledge that goes in. And this leads to, I think, what the weaknesses of current classical simulation techniques, in the sense that they're not very robust. What works for one system, it may not be the thing you do in another system. Okay, so where are the possibilities for quantum advantage? Well, I used up, wow, time just flown by. Okay, well, I guess I'll just give half my talk. So I'm going to go out on a limb. This is my kind of personal opinion. So if we ask, is there going to be an electronic structure problem in some real system where all methods just don't give any useful information, all classical methods? I personally think that's unlikely. I've not seen an example of this in the domain of chemistry and material science. I think that when one goes into physics, one can create some more artificial cases, or at least that are not constrained, where you can do this. But in chemistry and material science, I think it's very difficult. But that's not how we think about developing methods in the classical setting. I mean, we don't try and find a method that just beats everything else for everything. What I think is more likely is that just quantum algorithms, I mean, they will just introduce sort of new axes of complexity by which we can classify problems. And I think the thing that I think is most interesting to me is that I think quantum algorithms have the potential to be more robust in the sense that if one is looking not to use as much heuristic information and as much empirical information that we currently use in the classical world to get to these quantum solutions, I think that is possible in the quantum realm. I mean, a simple example of this is, if I want a completely robust classical method, exact diagonalization is the only one. You don't need any empirical information. Just do the thing. And it's, it's exponential in time. And if you do quantum phase estimation, if you also include the cost of state preparation, well, that arguably that's also exponential in time, but it's certainly not exponential in memory. And so, that gives you, an immediate advantage over what we do in the classical field. Okay, so then let me now kind of move and actually talk about some science. Okay, so now I'll move to address the second question about how we can maybe design some robust algorithms that we can use on NISQ devices. Robustness here doesn't mean robustness necessary to noise. It just means robustness to needing to input a lot of empirical information. Okay, so I'm going to focus on algorithms for ground states, just in the interest of time. And naturally, one can do phase estimation. We all know that. You just measure the Hamiltonian in essence, and that will give you the ground state with some probability if you do the state preparation. And the issue with phase estimation, though it's a very robust algorithm in the sense that I mean robust, it's not a NISQ era algorithm because you need a lot of controlled circuits, or at least not the current NISQ era. So I think everyone knows that. So typically, when one's talking about ground state algorithms, one's discussing variational techniques, QAOA, QE, and so on and so forth. And these are based on the idea of just optimizing the energy of a unitary circuit. And this is naturally something you can do in the NISQ era because you can make your circuit very shallow. But I would argue, at least to my taste, algorithms of this sort don't push us very far along this robustness axis. I mean, they may have other advantages, but one still has to design the circuit in practice, especially if you only have limited resources. You can't make your circuit arbitrarily deep, and then you have to think about how you put it together. And then secondly, you have to do this noisy, nonlinear classical optimization. So in classical simulations, one's always dealing with nonlinear optimization, and you have to use empirical knowledge to do it efficiently. But in this case, I feel, one has the same sort of issue that, it's not worse than classical algorithms, but one has the same sort of issue. Okay, so what we tried to do was to think of a different way to get to the ground state that has a kind of more robust feel to it, but which isn't phase estimation, which you can do in the NISQ era. And to do this, we took some inspiration from how classical exact algorithms actually work. So if you want to find the ground state exactly in a classical problem, one technique is to project out the ground state by doing imaginary time evolution. So you just cool the system in some way, in some sense, down to the ground state. Another related technique is to use things that we call Langstroths and so on and so forth. So this is where you build a space of vectors which are rich in the extremal vectors by multiplying the Hamiltonian onto the state, and you diagonalize the Hamiltonian in the subspace. This can be viewed as a polynomial approximation of this exponential. So these are sort of robust ways of getting to the ground state. But the classical bottlenecks are that you have to store the state, and that's exponential equal to cost, and you have to manipulate the state, and that's exponential in cost as well. And so what we tried to do was we tried to move these exponential bottlenecks onto the quantum device with NISQ-like techniques, and this is what gives us quantum imaginary time evolution and quantum Langstroths. So because there's not a great amount of time, I will just summarize what some of the properties of these algorithms are before explaining how they work. I think the nice feature of these techniques is that they're guaranteed to reach the ground state. So one doesn't have to worry about optimization. I think for me that's at least an important component. And then under certain conditions, the cost of doing an iteration of this technique is polynomial in the number of qubits. I mean, of course, this cannot be true in general, but under certain constraints of bounded correlations, then this is true. And so then this is an exponential speed up over the classical version of this algorithm. And then finally, there are no deep circuits, and so it's something that I think we can do in the NISQ era. So the heart of the algorithm is just this non-unitary operation, which is this imaginary time propagation. And one knows how to do non-unitary operations on a quantum computer. I mean, you can basically try and take a unitary operator and define it with some ancilly, and then measure and do some post-selection, and then you basically get the non-unitary operator out. But there are some issues with that, and doing a lot of these in a row, a lot of post-selection obviously leads to an exponential failure rate. So we came up with a different strategy to handle this non-unitary, which is based on the idea that in a non-unitary operator, all we really care about is not the whole operator itself, but just the action of the operator on the particular state that we're in, because we're just trying to track how this non-unitary operator guides the state down to the ground state. And so the action of a non-unitary operator in a state is that it just rotates the state and it rescales it. Okay? So a non-unitary operator acting on a state is just some rescaling factor times a unitary on the state. And so the basic idea is that we do some type of tomography in order to get out this rescaling constant and what this unitary really is. Okay, so I'll illustrate how we can do that for 1 qubit, and then I'm just going to say that's possible since we're going to run out of time. So in 1 qubit, for example, this is an action of the imaginary time operator for very small time on the state, and it maps onto a constant times a unitary times a state. And you can see immediately this constant is just a normalization constant of this object, so I can just do some measurements in some NISQ-like way, it's measuring expectation values to get this number. And then similarly, this unitary here is parameterized by 3 angles. And so I just need to do 3 measurements on the state to get the 3 angles. And so we just carry out 3 measurements and solve some linear equations, and then we can get the 3 angles out. Okay. So we can reconstruct the unitary in this way. And so this follows with more qubits in the general case. And you basically trotterize your Hamiltonian, apply it to a state, and then if the state has certain length of correlations in it, then we do tomography over the correlation size of the state, and we can, by linear algebra, reconstruct the constant and the unitary. Okay, so I'll just show some results since we're running out of time. Just to show that this could be done on a NISQ device, this was an implementation we did on Aspen-1. So this was really a very old chip of Rigetti. I mean, I don't think Rigetti themselves would say this was a particularly good chip, but it's a chip. This is just to show you that one can, in fact, propagate in imaginary time to get the ground state after some number of time steps. There are very large error bars because this is drift in the device. So if you run it several times, you get different results, and that's the error bars there. And I didn't tell you exactly how this can be done, but you can use this algorithm also to do statistical mechanics. And so we computed here some thermal expectation values. Okay. So I think that this is an interesting algorithm in the NISQ era in the sense that if one does resource estimates, it's actually very resource efficient, both in terms of the circuit depth and in terms of the number of measurements you need to reconstruct the unitaries. Here are some sort of estimates just on some very simple systems, right? So this is like a 4-site Heisenberg model and a 6-site Heisenberg model, and we compared it to the hardware-efficient variational ansatz, and we counted the number of measurements we needed to converge the VQE to 1% of the exact energy, and the number we needed to converge QITE to 1% of the energy. And you notice here that there's certainly far fewer measurements that are used in QITE, and this discrepancy gets bigger as the system size increases, and that's really the cost of optimization. At least our experience with VQE is that if you go to more and more sites, then the time to, the number of optimization steps to optimize the circuit also increases. So potentially this is something that we can scale to large NISQ devices. And here are just some kind of resource estimates or some ideas of how this might perform. So if we take the minimal formulation of this algorithm, one sees that it doesn't degrade in terms of its accuracy as the number of sites increases, and that one can get to quite a good answer just with a small number of time steps. Okay, so this is just applying 4 steps of imaginary time evolution. It's a very shallow circuit. And then secondly, is it robust with noise? Well, I mean, of course it gets worse as you add noise, but it doesn't completely fail. So these are highlighted here, some 1 and 2 qubit depolarizing channels, and one, introduces some error in the energy, but it's not too large. Okay, so based on these estimates, then if one was doing a simulation of 50 qubits to do 4 time steps like this, then this is 24 layers of CNOTs, which may or may not be doable, but presumably will be doable at some point in the future. Okay, so I think I've used up all my time, right? So I won't really talk about physical quantum supremacy. It's just really just one slide. And I just want to say that Bella, Sergey, myself, and Mario wrote a review article which is intended to give some perspective on quantum computing and quantum algorithms, mainly for chemistry and material sciences. But it might be interesting for you guys to read to get to see what it's like, from the other side. And so thank you for your attention.
Go eventually. So.
You talked about DMRG methods for transition metal complexes early on. Have those been applied to periodic systems of transition metals, like transition metal oxides and stuff, and how successful has that been?
Yeah, so DMRG, I mean, you could apply it to transition metals, but I don't think it in periodic systems, for example, using codes we already have, you can run such simulations. But I don't think it's really the method of choice there. Yeah. So the answer is there are codes to do it, but there are other classical techniques which are more relevant for that case.
On your 2-qubit QITE experiment,
Yeah.
when you were computing the unitary and getting the coefficients for the unitary,
Yeah.
did you use a classical linear optimizer, or were you doing it by performing the measurements of those?
Yeah, there's no optimization. Well, I mean, you perform some measurements, you construct a linear algebra problem, AX equals B, which you solve on the classical device,
Okay.
right? Just by exact linear algebra.
Okay.
Exactly.
Yes, actually, I wanted to ask you, if you had the time to talk about supremacy, what would you have said?
Well, I mean, okay, so roughly speaking, I'm just trying to say that I think most states that we usually think about are too easy. So the problem that I'm aware of in chemical physics is that is closely related to supremacy is the onset of quantum chaos. So if you go into molecular vibrations, you go up into the spectrum. So there's a question, at what energy scale do you actually get into the chaotic regime? And this is something that was studied a lot in the 80s. But of course, only in small systems because there's a limit to what you could simulate numerically. And so the key thing is to formulate studying this question in a way that can be done in the NISQ era. And I think that can be done really by trying to determine the unitary that transforms you to the energy basis in a variational way. And this gives you, by optimizing this object here, which is something people do in studies of many-body localization, they try and optimize this to diagonalize the Hamiltonian. You could try and do this on a quantum computer. This gives you a metric. You can get a number here. If quantum does better than classical, then you can call that supremacy, right? So that's kind of the story of that. Very, very briefly, yeah.
So the tomography step, is that exponential in the size of the largest correlation in the system?
Yes. Yeah, there's always going to be an exponential somewhere, right? Because it's ground state algorithms. Yeah.
The convergence of the imaginary time method probably depends on the gap, right?
It depends on a more complicated quantity than the gap. But yeah, you can get some, but that's a reasonable starting point. Yes, it depends on the gap.
This is system dependent. So
Correct,
how much
yeah.
do you expect this to be a problem for different systems or larger systems?
Well, I mean, if you study a gapless system, then you have to project to more imaginary time, right? That's the answer. It converges exponentially in the size of the gap. So I mean, the same thing is true in classical algorithms. You need to take, so you could imagine if this were not an issue, then you could just get to ground states, in finite amounts of time. So there must be problems where this gap issue is a problem. It's a little bit like adiabatic algorithms. There is a similar. It's not exactly the same, but a constraint there. But I'd argue that you don't need to think about it. I mean, you just run your algorithm, you just run it a bit longer and see if it changes. And that's the sense in which it's, I feel, robust. You know? I don't need to think. Yeah.
I mean, isn't the physics point of view that these problems are pretty generic because outside of one dimension, as you cool down, you'll encounter, some low temperature phase transition.
You mean, is it the case that everything is gapless?
Basically, outside of one dimension, as you cool down from high temperature, right, you expect some
Oh yeah, so this isn't the same as the adiabatic algorithm where you don't require any crossing of states, right? But it's certainly not true that everything is gapless outside of one dimension.
no, I don't mean gapless. I mean that there's a thermal phase transition out of the high temperature phase into something else where the correlation length blows up. I mean, it'd be nice to see, I guess, a general class of examples outside of 1D where this could
Yeah, yeah. I mean, so, one can always define cases, of course, where this is exponential cost. This is not a statement that one can always get to the ground state in polynomial cost, and that would violate a lot of things we think about complexity. The question is just whether this is true in typical materials, right? And I would argue that's not true in typical materials. Actually, in most materials, you don't go through any, you go maybe just through a disorder to order phase transition, but you don't go.
Does it blow up?
The correlation that could only blow up in certain types of phase transitions, right? They have to be second order. Right?
There's a question in the back.
Yeah, so you're making these strong correlation length assumptions on all the states in your algorithm for the tomography step to be sort of fast.
Yeah, along the path, right? Yeah.
Right,
So there's like no second order phase transition is for it to be an exact algorithm with this polynomial guarantee. Yeah.
Right, so I'm worried that if the states that you encounter in this algorithm really do satisfy that assumption, that's exactly the sort of property that would lend the algorithm to be able to be classically simulated.
Yes, yes. I mean, this is of course always a concern, right? I mean, so whenever you find some special subclass that seems to be, efficient classically, quantumly, even with factoring, right? Then you'll be like, well, but are you really sure there isn't a better classical algorithm to do so? What we did in the paper was we tried to identify, various types of classical algorithms that you might use. For example, let's just simulate on a finite chunk of stuff, right? That's one way. If you have a finite correlation length, you might expect to be able to get an answer for the whole piece. But you can construct counterexamples where that classical algorithm will fail, where it would appear that this one does not, right? So, but indeed, you always have to think about these concerns, yeah.
The Lanczos method you mentioned is actually pretty flexible when it comes to input states.
Yes. Yes.
You capitalize on that?
You mean that you can start from anything?
Yeah, basically.
Yeah, I mean.
To make it faster?
Well, we haven't done that type of optimization, but my argument for why I like this type of technique is because you don't have to think too much about how you do it. So indeed, we started from very trivial product states as our input states.